Good morning, namaskar everyone. My name is Dr. Safraz Ahmed on behalf of Department of Mathematics, Assam, Kaziranga University. I welcome our resource person, Dr. Diganta Borah, who is Associate Professor of IISER, Pune, most renowned institution functioning under the Government of India. He is working toward connecting young mind to stuff towards success and achievement. We are very grateful for him for accepting our invitation and become a resource person of the today's event. Dr. Borah does not require any introduction. He is a well-known figure in the field of mathematics. Though Dr. Borah received his PhD from Indian Institute of Science, IISER, Bangalore, India in 2010 and was a research associate there until 2011. He joined IISER Pune in January 2012 and his research area is several complex variables. I thank to my SBS Dean and HOD Department of Mathematics for giving me an opportunity to welcome all the aspirants in the second day of the International Conference. Thank you. Have a nice day.
Good morning, everyone. First of all, let me thank the organizers for giving me the opportunity to talk here. Especially during this pandemic time, it's very difficult to keep active. So it's really great job that they are organizing this activity. I'm going to talk on something called Weierstrass approximation theorem. Let me share my screen first. And also to keep the file size smaller, I'll keep my video off. Once I complete the talk, I'll show you my face again. Okay. Okay. I have shared my screen. Here it is. Okay. Okay. So the title of the talk is, as I said, Weierstrass approximation theorem. But before going into the statement of this theorem, let me, tell you what this approximation means in general. Okay. So approximation. See, roughly approximation means you want to replace a complicated object by something simpler. Okay, so approximation means replacing a complicated object by a simpler object. Okay. You are already familiar with this notion. I just need to remind you with some examples. So let's talk about some examples. See, in schools, we learn about the number pi, right? It's an irrational number, but for most of the calculations, we actually take an approximate value of pi, which is 3.14, right? This is an example of approximation. Pi is an irrational number. It's a complicated thing to deal with, but we use the approximation 3.14. Okay, that's a rational number to deal with many calculations. So let me give you another example. So when we talk about derivative, recall that derivative of a function at some point geometrically means the slope of the tangent to the graph of the function through that point, right? So let me draw a fixer. So So you have some, so this is y equal to fxa, and some point you want to, so this is the point a comma fa. So this is the tangent through a comma fa, and f prime a. So if, let me write down, if f is, so here f is, you can take for convenience r to r, is differentiable at a, then f prime a is the slope of the tangent. Tangent to the graph of f at a comma f. Right? This is something we are very familiar with. Now, you see, if you are very, very close to the point A, something very, x is very, very close to A, then this tangent line is nearly equal to this graph of the function. Right? So this part of the line, if you are very, very close to A, then this tangent line segment approximates the graph of the function. Okay, from the picture we see that. But what is the equation of the line segment? So the equation of tangent line is, so this is a line passing through a comma fa, and with slope f prime a, right? So we know the equation. So this is y equal to fa plus the slope is f prime a x minus a, correct? And because this line segment nearly equal to the graph of the function, so we have f of x is approximately equal to fa plus f prime a plus into x minus a for x near a. Okay. So this is linear approximation that you learn about the differentiable functions, right? So the right hand side, look, this is a linear polynomial, right? First order polynomial. Okay, then in calculus you also learn about something called Taylor's theorem, where you learn to approximate a function by higher degree polynomial. Okay, so let me quickly recall the statement. It says that so this is Taylor's theorem. It says that if f is say f from AB to R is such that scalar derivative is continuous on the closed interval AB, and its k plus 1 derivative exists on the open interval AB, then you can expand fx as some kth degree polynomial plus some remainder. Right? So let me not worry about the remainder. So I'll just write fx is approximately equal to, forgetting this remainder. And the kth degree polynomial is this is the Taylor polynomial, fa plus f prime at a into x minus a plus f double prime at a by factorial 2 into x minus a squared plus so on up to fk at a by k factorial x minus a power k. Okay, I am just leaving the reminder. Okay. So this is another example of approximation you are familiar with. Then, in other branches of science, most of the time we use actually approximate values rather than the original value. For example, see, if I ask you what is your weight, you would say 65 kilo or maybe 70 kilo. You're never going to say 65, your weight is 65.234 kilo or 70.125 kilo, right? You just give me an approximate value because most of the time that value is easy to deal with and that suffices. Okay. The only thing you should keep in mind is that in approximation, the simpler value that you are giving, the simpler object that you are giving should not be very far from the original object, right? For example, you see, let's recall the approximation of pi. So we use 3.14 as an approximation. 3 is also an approximation, but 3.14 is better because it is closer to pi than 3, right? In fact, you can get even a better approximation, 3.14 159 or something like that. So you can take even better approximations, right? So in other words, the difference between the original value and the approximated value, which we usually call the error, should be always small. Okay, smaller it is, you will get a better approximation. So the error in approximation, which is the original value minus the approximated value or the simpler value, this object should be small. You should always try to keep it minimized. All right, so this is a rough picture about what is approximation in general. Okay, I am now ready to state the so-called Weierstrass approximation theorem. Okay, so let me write down the statement first. So this is Weierstrass approximation theorem. This was first established by Carl Weierstrass. So this was by Carl Weierstrass. Around 1985. Okay. So what does the theorem say? It is the following. So let f from a b to r be a continuous function. then for every epsilon greater than 0, okay, you should think of this epsilon, given epsilon, as some error term. And given this error, I want to find, something, some simpler object whose values do not differ from f by more than this error epsilon. Okay, so let me also draw a picture. So you have a continuous function on AB. So this is, its graph is going to be nice. So let's say this is the graph of f. Okay, so y is equal to fx. And I'm given an epsilon. So what you do is you draw some tube, or rather band, around this graph of fx of width, say 2 epsilon. You draw it symmetrically. Okay, so something like this. So I'm drawing this band, and its width is 2 epsilon, right? So this is epsilon. So this is the blue line represents y is equal to fx. So the yellow line is the upper one is going to be, so y equal to fx plus epsilon, and this curve represents y equal to fx minus epsilon. Right? Good. So now your job is to find some simpler object which remains in this tube, and that's what Weierstrass theorem says, that okay, you can do that. So what it says, that the simpler object is a polynomial. So for every epsilon greater than 0, there is a polynomial P such that mod of fx minus px, this is less than epsilon, for all x in a comma b. Okay, so this is the statement of the Weierstrass approximation theorem. Now, some of you would be familiar with uniform convergence of functions. In terms of that, all you are saying is that this polynomial p is approximating f uniformly. Okay, so in other words, so I'll talk about this uniform convergence because I don't expect that everyone here knows this notion. So I'll just do that, but let me just write down the statement. So in other words, f can be approximated uniformly by polynomials. F can be approximated by polynomials uniformly. Okay. So which basically means that you have a sequence of polynomials that converges to f uniformly. Okay, so I'll briefly introduce this notion of uniform convergence, but before that, just let me give you a brief point why this approximation theorem is important. You see, polynomial functions are easy to deal with. They are among simplest functions. In fact, computing a polynomial is easier, right? Not only just computing the values of polynomial, rather if you want to differentiate or integrate or whatever. So these are easy to, so in those sense, it is polynomials are easy to deal with. You can in fact think of, suppose you are given an arbitrary continuous function. Although it is Riemann integrable, the computation of its integral need not be simple, right? You may not be able to write down you may not be able to explicitly compute the integral unless the function is very, very nice. But this theorem says that you can always find some polynomial near f, and computing the integral of the polynomial is very, very simple. Computer can do very easily, right? So this theorem has a lot of practical applications. It has also theoretical applications that you will learn later. Okay? So this is a very important theorem, a lot of practical and theoretical applications. So it's good to know this. So let me introduce, as I said, the notion of uniform convergence is being used here. So let me briefly tell you what does that mean. Okay, so convergence of functions. Okay, so there are two notions of convergence of functions. One is the first is the pointwise convergence. So suppose you have a non-empty set and very non-empty set, okay, and f is or rather fn from e to r. So for each say positive integer n, you have a function fn defined on the real valued function. Okay, so these are functions. Then we say that fn or let me write more details. So say that the sequence of functions fn converges to a function f from e to r if the following happens. So I'm going to the next page. So just let's remember the statement, whatever I have written. So you are given a sequence of functions from some set e to r, and I want to talk about limit of this sequence. So what I'm going to do, I'm going to say that, well, fn converges to f if the following happens, and here it is. Okay, so what you do if for each x in E, okay, so you pick up point x in E, and what you want is that, and then you evaluate the functions at this points. Okay, the sequence, fnx. So I have evaluated the functions at the point x. Now I have a sequence of real numbers, right? So the sequence is the usual sequence in R. All I want is that the sequence fnx converges to f at x. Okay, so you evaluate the functions at points of E, and you want that the corresponding sequences of real numbers converge to fx. So this is usually we write this convergence as, so that is limit n going to infinity, fn of x is fx. Okay. So for each x, this is happening. So we say that fn converges to f pointwise, or simply just fn converges to f. So let me give you an example to clarify this. So example, let's consider the following function. Say fn from R to R, and fn of x is simply x by n. Does this sequence of functions converge to some other function? It's easy to see this, right? If you fix some x and allow n goes to infinity, so x by n will become smaller and smaller, right? So it will eventually go to 0. So so note that so limit n going to infinity. So you take any point x, then this is actually 0. Okay, so fn converges to the 0 function here, pointwise. It would be good to keep some picture for this example. So you can also see this symmetrically. So what you do is, so let's draw the graph of this function. So you have, say, let me choose a different color. So fn is simply x by n, right? Or rather, let's draw f1 first. F1 of x is just x, the identity function. So it's the graph is y equal to x. Okay, and in general, fn x here is the line through the origin with slope 1 upon n, right? So you even if you take a bigger n, so you get something closer. Its slope will be closer to 0. So you have lines like this. If you take n even bigger, then 1 by n is smaller, so you have a line, something like this. Okay, so this is f1. Maybe say this is f half. So if you take n bigger and bigger, so these lines are, you see, geometrically also you can see that they are converging to, in some sense, converging or approaching to the x-axis, right? Y equal to 0 line. So geometrically also you can see that these functions are actually converging to the 0 function. Okay, right. So this is fn. Let's also keep another example in mind. So I take the second example as say fn from, maybe I will walk with the interval 0, 1 to r, and fn of x is x to the power n. Okay. How does the graph of this function look like? So you have x and y axis, and so this is 1. So it is going to look like something like this, right? At 1 it is 1, at 0 it is 0, and then so these are kind of more or less like parabola, but you have a higher degree, right? Here x power n. So so if x is larger and larger, you are going to be like this. So the graphs are these curves. At x is equal to 1, again you have this line. So again you geometrically see that these curves are approaching the x-axis except for one point, which is x equal to 1. So this, because all the functions are 1 at this point, and if x is strictly less than 1, then you can see from the picture, or directly also, if x is less than 1, then x power n will converge to 0, right? So in this case, so if you look at the function fx to be 0 for 0 less equal to x less than 1, 1 at x equal to 1, then we can see that Fn converges to F pointwise. Okay, good. So this is the notion of pointwise convergence. There are some drawbacks of this convergence. Namely, it doesn't. This notion of convergence doesn't preserve certain properties, certain nice properties of functions. For example, you may have a sequence of continuous functions, and they converge say pointwise to some function. It need not be true in general that the limit is a continuous function. See, look at the second example that I have given you. So Fn is this exponent that is a continuous function, right? So look at this example. So this guy is continuous, but look at the limit. This function, limit function, is not continuous, right? It is discontinuous at 0. This is not continuous. 0 everywhere and 1 at 1. So not continuous. So if a sequence of continuous functions converges to some function pointwise, in general, it need not be true that the limit is continuous. So this is one drawback. There are many others. So in fact, forget about continuity. You may have a sequence of Riemann integrable functions converging pointwise to some function. The limit need not be even Riemann integrable. So let me give you that example also. So this is even worse because see, continuous functions are Riemann integrable, right? But Riemann integrability is a weaker notion. So Riemann, you have even this concept is not preserved under pointwise convergence. So here is an example to show this. How do I do this? So let's look at the following. So let's look at the rational numbers in the interval 0, 1. Okay, you can enumerate these rational numbers. You can list them, right? So this is enumerable set. So let Rn be an enumeration of the rationals numbers in the interval 0, 1. You list them. It is possible to do that because there is a bisection between the rational numbers and a set of natural numbers. So once you do that, so you define the function Fn from say 0, 1 to R by. So what you do, you define it to be say 1 if x comes from the first n rational numbers in 0, 1. So up to our enumeration. So say if x comes from R1, R1, R2, and so on, Rn. If x is one of this, you call it 1. Define Fnx to be 1, and 0 otherwise. So this is, you see, this function is 0 almost everywhere, 0 everywhere except for this finitely many points R1 up to Rn. So as a function is Riemann integrable, right? It has only finitely many discontinuity. So Fn is then Fn is Riemann integrable. Now let's see if we can find some limit of this function. So can you guess some limit for this function Fn? Well, if n is very, very large, well, in fact, you want to take n to infinity. So then you are allowed to take x to be anything from the rational, right? Anything from the set Rn. So the limit you can easily guess is that fx is 1 if eventually you will be taking all the rationals, right? X is in R1, all of them. Maybe or rather I should say x is rational. X is rational. And 0 if not, x is irrational. So this function, which is 1 at the rationals, 0 at the rationals, this is discontinuous everywhere. So this is not Riemann integrable. Okay, it is one of the first example of non-Riemann integrable function that you learn, right? So here of course you have fn. Fn converges to pointwise. So Riemann integrability is not preserved under pointwise convergence. So these are some drawbacks of pointwise convergence. You know why all these problems are happening is actually the following. So I am going to reformulate the definition of pointwise convergence. That will help you to come up with some definition for a stronger notion of convergence called uniform convergence. So reformulation of pointwise convergence. So you have a sequence of functions fn from E to R and a function f from E to R. Okay, so these are given. Then fn converges to f pointwise means the following. For each x in E, recall we should have limit n going to infinity, fn of x is fx, right? Let me put it inside a box. And if you recall the definition of convergent sequence, so this box is equivalent to the following. The statement is equivalent to the following. For or given epsilon greater than 0, there exists some integer, positive integer n, such that fn of x minus fx is strictly less than epsilon for all n greater or equal to n. Right? But the key point here is to note that, you see, first I fixed an x, and given this x, you take any epsilon, then you have some n. But this n now may depend on, this of course depends on epsilon, but this can actually depend on x also. Okay, so this n, so note, n depends on both x and epsilon. So in other words, if you go to a different point, say y, even for the same epsilon, you might have to pick some another capital N. Okay, the same n may not work for all x. That is the problem. Let me actually show you by an example. So let's consider the first example itself. So let's go to the page. So let's look at this functions. Fn of x, remember we defined fn from R to R, and fn of x we defined as x by n. And we saw that fn of x converges to fx is equal to 0 pointwise, right? We have seen this. Let me show you that if I take different points, then even for the same epsilon, you may not be able to find a single capital N. Okay, a single capital N may not work. So in fact, so let us show this by contradiction. So if possible, say assume that that say let's take some epsilon. Assume that for epsilon to be say half. Okay. There is a single N such that which works for all the points, such that so mod of so n greater or equal to n implies fn of x minus fx is less than epsilon. This is true for all x in R. Okay, so let's rewrite this. So that is so fn x is x by n and fx is 0. So the left hand side is simply mod x by n. This is true for all x in R. Okay. Well, if this is so for all n you have this. So in particular, I can take so for all n bigger than or equal to n you have this. So in particular, I can take n to be capital N, and then the statement should hold, right? So in particular, so because the statement is true for all n greater or equal to n. In particular, I should have mod x by capital N less than epsilon for all x in R. But this is not possible, right? I can choose some value, say if I take, so taking x to be say n, I get 1 to be, remember I took epsilon to be half, right? So let me replace epsilon to be half so that, so here I can replace it by half to look better, right? So if I take x to be n, then I get 1 to be less than half. This is a contradiction. So our assumption that a single n works for all x is cannot be true, right? So so you see in pointwise convergence, the capital N that you're finding, it depends on both the point as well as epsilon. You can check this for the other example also, the sequence of polynomials that I considered, fn x is equal to x power n, show that a single n doesn't work. You can do similar kind of work and see that. Okay, to overcome this, we introduce a new notion of convergence, which is called uniform convergence. So let me write down the definition first. So let E be a non-empty set and Fn from E to R. These are functions. Then we say that Fn, the sequence of function, converges uniformly to a function f from E to R if the following happens. For every epsilon greater than 0, there exists an integer n, positive integer n, such that n greater or equal to n implies mod of fn x minus fx is less than epsilon. This is true for all x. Okay, so I'm finding an and that this doesn't depend on points. So geometrically, it means the following. So if you think of this is the graph of fc, okay, and then given any epsilon, so basically you are drawing a band of v to epsilon symmetrically around the graph of f, like in a Weierstrass polynomial. I have already given you the picture. So you have this is f plus epsilon, this is f minus epsilon, right? So given this band, in fact, given any band, you would be able to find some stays capital N, such that after that onwards, all the functions lie here. So, so this fn's has to be in the inside. So this represents fn, this red part, okay, where n is greater or equal to n. So after some stays, the graph of all the functions fn will lie in this band. So this is what geometrically uniform convergence means. So as you can see, Weierstrass theorem now basically is saying that you have a sequence of polynomials that converges to f uniformly. Given a continuous function on a closed interval, there is a sequence of polynomials that converges to the function uniformly. Okay, this is what the Weierstrass approximation in terms of uniform convergence looks like. Good. So I should give you some examples of uniform convergence. So let me. So as you can see, the sequence fn x is equal to x by n. Look at the example on the left. That of course does not converge uniformly, right? Because here n depends on both x and epsilon. But the definition of uniform convergence is that you have an n that depends only on epsilon. But see, I can slightly modify this example itself to give you an example of uniform convergence, sequence of uniform convergence, sequence converging to converging uniformly. So let's take. So what I'll do. So let's take fn to be, say, from 0, 1 to r. I am modifying the domain of the function. So I take 0, 1 to r, but the functions are same, defined by the same formula. I change the domain. I am now in the interval 0, 1. So see, I have drawn you a picture, right? So you have something like this. So now I am focusing only on 0 to 1. Say this is x equal to 1, this is x equal to 0. So these are the graphs of the function. So geometrically also you can see that if you draw some, some band of say v epsilon. So here the pointwise limit is f is equal to 0, right? So if you draw something like this, this line segment will eventually be in here. Earlier, the problem was you have like the whole line, right? It will, so no matter whatever this kind of band you take, eventually the line will escape from this tube. But now you have like finite length, so eventually all these things will end up inside the tube. Okay, so this you can mathematically also verify that then Fn converges to 0 uniformly. Okay, let's for convenience, let's write down at least this example. So what do we have to show? So let epsilon greater than 0. We have to produce capital N such that n greater or equal to n implies mod of fnx minus fx is less than epsilon for all x in 0, 1. So let's rewrite. So that is n greater or equal to n implies. So fnx is just x by n, fx is 0. So you want mod of x by n to be less than epsilon for all x in 0, 1. But good thing here is that because x is coming from 0, 1, it is bounded by 1, right? And then if you choose n large enough, definitely you can, bound this thing. So in fact, from this, you can easily see that what n should work is, I want 1 by n to be less than epsilon. So you should take capital N. So you take n to be so greatest integer less than or equal to 1 by epsilon and maybe plus 1. Okay, right? So, or maybe you just find it correctly. Okay, so I might be so let's see. So if n is greater or equal to n, then this would imply that n is also greater or equal to 1 by epsilon, right? Plus 1. So I actually have bigger than. So this is bigger than 1 by epsilon, right? So n greater or equal to m implies n is bigger than 1 by epsilon. So 1 by n is less than epsilon. So this implies mod x by n, which is of course less than 1 by n because x is bounded by 1 is also less than epsilon. So I have shown you that n greater or equal to n implies this holds. This is for all x. So Fn converges to 0 uniformly. Okay. All right. So that's good enough. The fact here is that certain notions of good properties like continuity, Riemann integrability, these notions are preserved under uniform convergence. So uniform convergence preserve continuity, differentiability. Differentiability, you need some additional assumption. Riemann integrability. And differentiability with some additional assumptions. So we'll not talk about these things in detail. You will either you have seen this or you are going to see this. Okay, so but this is all I want to point out is that this uniform convergence is a stronger notion of convergence than pointwise convergence, and it preserves many good properties. So if you have a sequence of continuous functions, which converge uniformly to some function, the limit will always be continuous. If you have a sequence of Riemann integrable functions that converge uniformly to some function, limit will also be Riemann integrable. And in fact, you can, integral of fn's will also converge to integral of the limit. That is also you can check. All right, so this is good enough about uniform convergence. And now, this should be clear from the definition that the Weierstrass theorem basically is saying that given a continuous function, you have a sequence of polynomial that is converging to f uniform. Okay, that's what we have to establish. All right, so I should now try to give you a proof. I have enough machinery. But I'm going to, rather than writing down a particular proof, so there are several proofs, by the way, of this approximation theorem. I'm going to, write down a proof based on some nice concept called convolution, because that is useful not only for the proof of this, but also for various other things in mathematics or physics. So here is this notion. So this is going to, so this particular notion, this is going to help you in establishing various other approximation theorems. In fact, I'll prove a general approximation theorem, and then I'll show that Weierstrass theorem follows from that. So I need the notion of something called convolution. Okay, very useful concept in mathematics and physics. So what does it mean is basically this tells you how, a new way of combining two functions to get another functions. I'll briefly, talk about this notion. We will learn about this later. So suppose I have two functions. So let f comma z from R to R. So these are two functions. And then the convolution of f and z denoted by is the function so we define it as follows: f star of z at x to be integral minus infinity to infinity. It's an improper integral. F of x minus t. So x is fixed here, and gt, t is the variable of integration. Okay, so x is fixed here. Provided, so I am talking about an improper integral here. So I have to know that this the right hand side is defined, right? So provided the integral converges or exists. Actually, there is there are a lot of good functions. There is a class of functions for which the convolutions are always defined. I am going to give you a small class of functions. So remark. But you have a large class of functions that you will learn later. So so for this talk, this introducing those classes beyond the scope of this talk. But I give you a simple class of functions where this can always be defined. So suppose say if you have continuous functions for the class of continuous functions which vanish outside some bounded interval, closed intervals, they vanish outside closed intervals. Yes. So for different functions, you might have different closed intervals outside which they vanish. You don't have to have a single closed interval. Okay. The convolution is always defined. Indeed, you see, if f is a continuous function, that vanishing outside, say, AB, and z is a continuous function vanishing outside, say, some interval c comma d, then so and the definition of convolution, you see, I have to integrate something, right? So you fix an x, then you integrate the function f of x minus t gt, which is here. See? Then so let's see, for how does it look like? So for each x in R, so let's look at this object, f of x minus t zt. Okay, as a function of t, I want to integrate this, right? Let's call this as t. This is, you see, you are multiplying two continuous functions. So you have a continuous function. This is continuous. And also, because you are taking product f and z, so if one of them is 0, the product will be 0, and z vanishes outside some interval, right? C comma d. So and vanishes. So this product also vanishes outside c comma d. So if you this integral reduces to, so f of x minus t gt dt is simply you have to integrate on c to d f of x minus t, this continuous function. So this guy is simply h, right? ht. So this is a continuous function. So you want to integrate this continuous function on the closed interval cd. So that is always it will always exist, right? Exists. Okay, so this is actually a rather small class of functions where convolution is defined, but we'll be dealing with such functions. So I just wanted to remark that at least for this class, you have all those things. The convolution is defined, but in general, this class of functions where it is defined is actually much more bigger. Okay, but let's not worry about that. So we don't need that. Okay, so how is convolution going to help us? So. So before going into that, so let me recall certain properties of convolution, some easy properties of convolution that will be useful for us. So let's look at the definition, which is, so again, let's come back here. So f star of z is, say, f of x minus t into g. So you are integrating f of x minus t into g, right? X is fixed and you are integrating with respect to t. So suppose I make a substitution, namely u is equal to x minus t. So so you can do it in your own notebook. So if you substitute u is equal to x minus t in this formula here, the right hand side, so what does the integral become? So you have f of u, z of so u is x minus t, so t will be u minus x, right? Sorry, x minus u. T will be x minus u. And the integral of this limit changes, minus infinity to infinity will change to infinity to minus infinity, but dt is replaced by minus du. So finally, you are going to have, so maybe I write down. So let's write down. So you have f star of zx is minus infinity to infinity, f of x minus t, c of t, dt. So you substitute So u is equal to x minus t. So then this becomes f of u into z of t is now x minus u. You have dt is minus du, but I write it as du, and then again I put minus infinity to infinity. Okay. So this is nothing but this is z star f, right? At x. So convolution is commutative. Okay, so some properties I want to list on. So convolution is commutative. F star z is z star f, which I have just checked. Some more easy properties, I leave it. Actually, I don't verify all of them. It will take much more time, but they are easy to verify. So I leave it to you. Something like, so you can check that f star z plus s is f star of z plus, it's associative also. Sorry, distributive, not, this is distributive property. You can easily check that some constant time f star z is same as, you can take the constant out, f star z. Yeah, and by commutativity, you can again put alpha to g. So this is, alpha is a real number. You can also check associativity. It requires some more work, interchange of integral and all, but one can nevertheless verify that this product is associative. This convolution is associative also. Okay, so these properties can be easily verified. In particular, if you look at one is commutative. Look at the last one; it says associative. So you might get some questions in your mind if you have seen some group theory. So you might ask the question whether in the class of functions where the convolution is defined. So because now it is associative, commutative, etc. Do we have an identity so that we can talk about, so because group theory, for a group, we need identity and inverse, right? At least can we talk about some identity here? So is there an identity? So question, it's a natural question. Is there an identity for unit element? That is there a function delta such that delta star f is f for all f? Surprisingly, not surprisingly actually, the answer turns out to be no. No in general. No, rather no. I want you to think about this why. So you assume that this is true and try to see if you can get a contradiction. I'll not give you the why the answer is no, but you should definitely try. You might need some advanced analysis, but maybe if you are in the final year of your BSc or first year of MSc, you might be able to come up with an answer. Okay, so the answer is in general no. Okay, no issue. So we don't require that. But I'm going to show you that at least even if there is no identity, there is something closely related to it. I'll introduce this. So for this, I need a definition. So let me give you some definition. A Dirac sequence is a sequence of continuous functions so let's write it as Kn on R with the following properties. So first of all, I want this functions to be non-negative. So these are non-negative functions. So their graphs lies above the x-axis, right, or on or above the x-axis. Second, I want that the area under the graph of these functions is always 1. Okay. So area under the graph of Kn is 1 for all n. This is the second property. And the third one, so is the following. Let me see the numbering. Okay, 1, 2. So the third one is what I want is that. So as I said, area under the graph of Kn is 1. What I want is that the major contribution to area should come from the function near the origin. So which I write. So maybe I draw a picture for this and then write down. Then it will be easier to understand. So how does the Dirac sequence look like? So in practice, they're going to look like what I'm going to draw here. So let's take this. Something like this. So if k is so n is larger and larger, you are going to get something like steeper and steeper. Okay. Something like this. Okay, so these things will not be, can be like this. So what is happening is that you see the area under the graph of Kn. So this is Kn. If you take n larger and larger, so the major contribution of area comes from its values near the origin. Okay, so this is what I want to write down as follows. So we'll make it precise like this. So given epsilon greater than 0 and delta greater than 0. So epsilon you are thinking as small and delta is some number. So there exists some n in n such that n greater or equal to n implies. So I want to look at the area under the graph of Kn, but away from this, say, delta interval. So this delta is also given. Some small number is given and some delta is given. So if you are away from this, so the area outside this interval should be small. Okay, because most of the areas are concentrated near 0. So n greater or equal to m implies I want that. So integral of so the area will be now, so you are minus infinity to minus delta, right? Knx dx plus delta to infinity knx dx. Okay, so this represents the area outside this interval, minus delta to delta. So this I want to be small. For simplicity, I will write this as this, I will combine into one integral knx dx, and I will write it as here x is bigger than or equal to delta, right? Then you are outside the delta interval, minus delta and delta. So I'll write it as single object. Okay, this two integrals will represent the sum of these two integrals. Okay, great. So these are the three properties. If a sequence of continuous functions can satisfy, then I'll call them a Dirac sequence. So in practice, their graphs looks like what I have drawn on the right. Usually they are symmetric with respect to the y-axis also, and they're kind of even functions satisfying these properties. And why? So I will write down one example, explicit example. So define Kn from R to R by, so Kn of X, say, so what you do, so let's do the following. So I first of all, I make it 0 outside, say, mod X greater or equal to 1. Okay. And so inside -1 to 1, what I will do, I will look at 1 minus X square power n. Okay, so this is inside this interval, -1 to 1. So mod X greater or equal to 1. Right. So at at 1, the 1 minus X square is 0. So this is continuous. Right? Continuity is not a problem. But I'm going to need integral of Kn to be 1. So I'm going to put some constant here. Okay, so that integral becomes 1. So where Cn is, so if I want integral of Kn to be 1, I should take the Cn to be integral of, sorry, -1 to 1. Okay. Right, if you take Cn to be this, you see integral of Kn is, because of our choice of Cn, so it is like Cn by Cn. So so integral of Kn is the Cn by Cn will be 1. Okay, so then of course Kn is greater or equal to 0. Integral of Kn is 1 by our choice of Cn. The third property is, again, you see, if you are away from 0, then 1 minus X square is strictly less than 1, right? Outside interval -1, 1, anyway, it is identically 0. But inside -1 to 1, and if you are, away a distance, positive distance away from the origin, 1 minus X square is strictly less than 1. So if you take high powers, that will be, very, very close to 0. You can use these ideas to verify that 3 also holds, but I leave it to you because it requires some computation, but they're easy. Okay, so this also holds. This is an exercise. You should check this. So this is an example of a Dirac sequence. This sequence is usually called Landau sequence. Okay, so Kn is called Landau sequence. It's an example of a Dirac sequence. Okay, so far so good. I should be, moving into the proof of the Weierstrass approximation theorem. But as I promised, I am going to first give you a general approximation theorem, which will immediately apply the Weierstrass approximation theorem. So theorem. So let f be a continuous function on R, vanishing outside an interval, closed interval a comma b. Outside this interval, f is 0. Inside, it's something. It could vanish also, but we don't care. At least outside it is 0. Then, if Kn is any Dirac sequence, then Kn star f. So this sequence of functions converges back to the function uniformly. Okay, so you take any Dirac sequence, K in star F is going to converge to F uniformly. Important, okay? Not just pointwise, but you have uniform convergence here. The proof is very, very simple, but I need to use some properties of continuous functions that you learn in calculus. I just quickly, write down those properties before going into the proof. So some properties. Continuous function that we will use. So the first one is the following. If you have a continuous function on a closed and bounded interval, then the function is bounded, right? If f from, say, closed interval a, b to r continuous, then f is bounded. That is, then there exists some m in r, such that mod of fx is less equal to m for all x a, comma b. Okay, so this is, all of you know. Another property is that if you have a continuous function on a closed interval, then it is uniformly continuous. So if f from a comma to r, so this closed interval is important here, okay, in both the properties. If you have open intervals or not closed intervals, it's neither be true. So f from a, b to r is continuous, then f is uniformly continuous. What does it mean? Let's recall it. So given epsilon greater than 0, there exists delta greater than 0, such that mod of fx minus fy is less than delta whenever x minus y is less than delta. X, of course, xy coming from AB. So this is uniform continuity, right? It's stronger than continuity. Recall, what does continuous function means? You take a point, you take a epsilon, then you have a delta such that something like this holds. But the delta depends on, both x and epsilon, both the point and epsilon. Whereas here, you see, given an epsilon, I am able to find a delta which does not depend on the point x or y. Okay? The moment 2 points are close by delta distance, then fx minus fy are close by. Sorry, so I did a mistake. So this is epsilon. Okay. So this is so the fx and fy are close by epsilon. So this is how uniform continuity is different from just continuity. It's similar to the notion of convergence and uniform convergence. So the role played by n there in convergence is being played here by delta, right? So there, uniform convergence, you are able to choose an n independent of the points. Here you are able to choose a delta independent of the points. Okay, so you should compare these two notions. I'll not go into the detail, so I don't need anything apart from the definition of uniform continuity, but it's a stronger notion than continuous functions. Okay, so these are the property I will use to prove this general approximation theorem. Namely, if you have any Dirac sequence, then k in star, this continuous function on closed interval AB, continuous and vanishing outside AB, will converge back to the function. So let's try to write down a proof for this. So proof of the theorem. All right, so what do I have to do? I have to show that k in star f and f, I can make it as small as I want. So first, let's write down, how does kn star f and f looks like. So I want to, estimate this difference, kn star f x minus fx. So how does it look like? So kn star f by definition, minus infinity to infinity, kn x minus t, ft dt minus fx. So somehow I have to combine them and make it small. So what I'll do, so first of all, you see what I'm going to do, because convolution is commutative. So first integral, I write it as kn t f of x minus t dt. Okay, we have already seen that convolution is commutative. You can do that. Second, because I want to combine this first term, which is an integral, with this number, I'm going to use some property of kn to write it as an integral. See, integral of kn is 1, right? So I'm going to introduce this kn t dt. Because simply I'm multiplying by 1, so I'm not changing anything, right? This integral is 1, so nothing is changed. But good thing is that now I can write it under one integral, minus infinity to infinity. You have f of x minus t minus f of x and k and t dt, right? Good. So this immediately gives you some idea. So because f is continuous, f of x minus t minus fx will be small if x minus t and x are close by. That is if t is small, right? So I'm going to use that idea nicely so that I have, I can establish the uniform convergence. So the major point here is that this is small. Okay, so this is what I am going to use in a clever way. Okay, so let's go to the next page. So, but I should, okay. Let me keep the formula here. So we have just checked that kn star fx minus fx I have written in the following form. I will need this f of x minus t minus fx kn t. So here x is fixed, by the way. I have fixed an x on the interval AB. I want to show that the uniform convergence on AB, right? So x is coming from AB, and then I have this formula. Okay, now to make this small, so let epsilon greater than 0 be given. So okay, this is given to me. I have to find a capital N such that mod of kn fx minus fx is less than epsilon whenever n is greater or equal to n, right? So I'm going to estimate this, and I'm going to find this n by means of different work. So first, what I'll do, since f is, so first thing to note that since f is continuous on AB, as I said, it is uniformly continuous. Right? Also, outside AB, f is identically 0. So you can actually check that f is uniformly continuous on all of R. Since f vanishes outside A comma B, f is uniformly continuous on all of R. You can easily check it from the definition, so I leave it to you. So what does it mean? Now I have a given epsilon, so there it is. So therefore, there exists some delta greater than 0 such that f of x minus fy, this is less than epsilon whenever x minus y less than delta. So if 2 points are close by delta distance, then the values are close by epsilon. So But here in this formula, you see, I have f of x minus d and fx. 2 points are x minus d and x. So let's write in that form. Okay, so if x minus d and x, so their difference is simply t, right? So in particular, so or I can say that f of x minus t minus f of x, this is less than epsilon whenever mod of, so here x is x minus t and y is x, so their difference is t. So if t mod t is less than delta, then you are going to have this. Okay, I'm just rewritten the previous line in terms of this new line. Good. Maybe so for convenience, what I can do, I am going to do the following. So I'm going to take this place equal to, okay, so it's not, it's it doesn't say anything. Okay, you can take x minus y to be, you know, if you necessarily, you can modify the definition, or you can take a smaller delta to, right? This is going to help you with integration, because I'm going to involve the endpoints. Okay, so but it's a minor thing, it doesn't harm anything. So anyway, so so coming back to the proof now, what I will have is the following. So what I am going to do, I am going to rewrite this integral on the left into two parts, right? You know, this integral. So rather you know, let's minimize our walk. So kn star f x minus fx. So this is one integral, which is here. I break it into two parts. One is, you know, when mod of t is less equal to delta, and the integral you keep as it is. So this is f of x minus t into minus fx into knt dt, plus the other part mod t greater or equal to delta, f of x minus t minus fx knt dt. So I break down into two parts, and I'm going to show that each of them is small. Okay. Let's first walk with the first part, because you see there mod t is less equal to delta, and I already have some estimate for that. Okay. So first thing to note is that mod of the first integral, f of x minus t minus fx knt dt, this is less equal to, I take the modulus inside first, and then you see mod of fx minus t and fx, that is because mod t is less equal to less, this is less than epsilon. And then I have this knt dt. Okay, but this, what I can do, I take the epsilon out. So you are integrating now kn on this minus delta to delta, but that will definitely less equal to integral of kn on minus infinity to infinity, right? So you're integrating on a bigger interval, the same non-negative function, so the value will be bigger. The advantage here is that because of the second property of the Dirac sequence, so this is, the integral is 1, so this is simply equal to 0. So first term I could make it smaller than epsilon, right? Thanks to the way I have chosen this delta. Now let's see what we can do with the, you know, second term. So let's okay, for the second term, so second term was integral of minus, sorry, this was outside the interval, delta interval, right? So f of x minus t minus fx into k and t. This was the second term. Okay, let's keep it here. I want to make this also small. So how do I do this? F, first of all, because f is a continuous function on the closed interval AB, outside it is 0, so it is bounded, right? On the interval AB, it is bounded by m, but outside it is 0. So I am going to use that fact. So there exists m such that mod of fx is equal to m for all x in R. A priori, it is true on the interval where it is continuous, closed interval AB, but outside it is anyway 0, so this has to be true everywhere. Right? So this is one thing. The second, Kn being a Dirac sequence, we know that the area under the graph of Kn, so this is usually considered near the origin, right? I am going to use that property here also. So given the epsilon and delta that I have already found, so there exists some capital N, such that n greater or equal to n implies integral of k and t, so mod t greater or equal to delta is less than epsilon. This is the third property of the Dirac sequence. I have started with some epsilon. I have found some delta that helped me to make the first term small, the first integral small, and then I am going to make the second integral small using the third property of the Dirac sequence. So which is this, right? So let's combine this. So then, okay, therefore, the second integral, so mod 3 greater or equal to delta minus fx k and t, right? Dt. This is less equal to. So I take the modulus inside. Then the first term, which is f of x minus t minus f. So that is because f is bounded by m. So I can, by triangle inequality, it is bounded by bound of f and f. So this is 2m. So that will come out. And then you have integral of mod 3 greater or equal to delta k and t dt. So dt should be here also. Okay. And this is because of the so I should write n greater or equal to n implies I can then make it less than epsilon. So 2m times epsilon. Second integral, I could make it less than 2m times epsilon. So combining, so what we have proved now, so thus we have mod of kn star f minus fx. This is less than or equal to, what we have proved is that, so first term was less than epsilon. The second term I have proved it to be this. So this is, you can write it 1 plus 2m into epsilon. And this is, we have proved this to be true for all n greater or equal to n. Thus, n greater or equal to n implies this. I wanted to make it less than epsilon, but I could show that it is less than 1 plus 2m by epsilon. That's okay. You see, because I can change. So you start with some epsilon, and you. So here, for example, I can make it. I can replace this epsilon by epsilon divided by, say, 1 plus 2m, right, or 2 times 1 plus 2m. So I can replace this particular epsilon by epsilon divided by some constant, the starting epsilon. Similarly here also, so the first term where, yeah, so this here also I could have made I could have made the, this particular term less than epsilon by 1 plus 2m. This is a standard trick. Okay, so you start with some epsilon and then replace the remaining epsilons by modify it accordingly. So finally then you end up with less than the original epsilon. So it's a standard trick. So what you required to prove is actually been done. Okay, so this proves that thus Kn star f converges to f uniformly. Okay. This completes the proof of general approximation theorem. So you have any continuous function on a closed interval, and when it is outside the interval, and you have any Dirac sequence Kn, then you have Kn star f converges to f. So in other words, Kn star f approximates f, uniformly. So see, I asked the question whether there is some identity or not, and I also say that there is no identity. But a Dirac sequence, this theorem basically says that a Dirac sequence is kind of, it is approximation to identity, because in the limit, what you have is that Kn star f in the limit is f. You don't have delta such that delta star f is f for all f, but you have if you take a Dirac sequence, it acts like approximation to identity, because in the limit Kn star f is f. Okay, so Kn, a Dirac sequence, thus a Dirac sequence is an approximation to identity. To the identity, because in the limit it behaves like identity, right? Great. So the general approximation theorem is done. It's very useful in approximating various things, but we want to see a particular application only to the Weierstrass approximation theorem. Nevertheless, it is very useful, as I said, in other approximation results also. That's the reason I have given you first the general proof. Okay, so so finally, I will very quickly finish the proof of the approximation theorem. We don't need much work now. Okay, we are almost done. I'll stop soon. Okay, so, but let's complete the proof. So, proof of Weierstrass approximation theorem. So remember, what does the statement says? You have a continuous function on a closed interval. You can approximate it by polynomials uniformly, right? That is, you can find a sequence of polynomials converging to the function uniformly. Now, so to make the exposition as clear as possible, so I'm going to first stick to a very special case, a special case. So which is namely, we assume that a comma b is the interval 0, 1, okay, and the function f, the continuous function f, vanishes on the endpoint. So f0 is equal to 0 is equal to f1. So this is the special case. The general case can be very easily obtained from this. So I'll in fact point it out after this is done. Okay? So we have a continuous function now on 0, 1, and we want to approximate it by polynomials uniformly. So what I'll do, first define f to be 0 outside 0, 1. So I want to extend first of all f to all of r. It is a priori given on 0, 1, and we are assuming that f0 and f1 are 0. So I define it to be 0 outside 0, 1. Now I have a function on all of r, right? Good. Also, now let's. So what I'll do. So let's consider the Landau sequence. Remember, this was defined as Kn of x to be 1 upon some constant times 1 minus x squared power n when mod x is less equal to 1, and 0 when mod x is greater equal to 1. So this is, we have observed that this is a Dirac sequence, right? Now the general approximation immediately implies that by the previous theorem, we have Kn star f converges to f uniformly on the interval 0, 1, because f vanishes outside this, right? F I extended to be 0 outside this interval. So the general approximation theorem applies, and I have a uniform convergence here. So what do you need to show? Remember, the statement says that you have polynomials approximating f. So if I can show that this convolution Kn star f actually is a polynomial, then I'll be done, right? But so let's compute this thing. What does it look like? Kn star f at some point x in 0, 1. So this is by definition minus infinity to infinity Kn of x minus t, ft dt, right? This is, but you see f vanishes outside 0, 1, so I can reduce this integral to just 0, 1. Then Kn of x minus t, so Kn is just a, on 0, 1, it is just a polynomial, so it is 1 upon Cn. And then you have 1 minus x squared, so here x minus t squared power n. This is Kn of x minus t. And then you have ft dt, right? You need some computation here. You see this, you can expand using the binomial theorem. So if you expand, you get a polynomial. Polynomial now in x and t. Okay, so I in fact combine all these terms. So this can be written as, so you are going to get some polynomial. So this is summation over I comma j, but it's a finite sum. And you will get some x power I into y power, not y here. I have t power j. So if you expand the first term, you have something like this, a polynomial in x and t. And then you have ft dt. Okay, I'm almost done. So what you can do now, you are integrating with respect to t only, right? So anything which is free from t, you can bring it outside. So this summation will come outside. This constants, this will come outside IISER, and then x power I will come outside. So, and then you will be left with integration 0 to 1 t power j ft dt. Okay, but this is again some real number only, right? T power j ft dt, and of course it will depend on z. This thing will be, so you can call it some, say, bj. Okay, so this, call it bj. Then you have the summation aiz bj. If you combine, so you can just sum over j first. So all you will be left with, so this is equal to summation some, say, I have already used a, b, maybe c, so some d I xi. So this is of this form, summation of I. So it's a finite sum again. So this is a polynomial. So k, and thanks to this or choice of k. So when you convolve with this continuous function, you actually get a polynomial. So this is a polynomial, right? And then you are done, right? So you have Kn star f approximates to f uniformly, and Kn star f is a polynomial. So I have shown you that there is a sequence of polynomials that converges to f uniformly. That is the, that is what the Weierstrass theorem says. So that is the proof of the Weierstrass. Very simple once you have the general approximation theorem. Okay, so but I have worked with a very special case, namely the function is defined on 0, 1, and it vanishes at the endpoints. Let me show you how do you tackle the general case. Okay, and then I'll stop. I'll just take just 5 more minutes. Okay, so general case. First let me, get rid of the assumption that the function, varies at the endpoints. Let me still work with, continuous function on 0, 1 only, f from 0 to 0, 1 to r continuous. But I no longer assume that the function vanishes at the endpoints. Okay, then I will go to a general interval. So how do you do it this case first? So I don't have, f0 is 0, f1 is 0. So what I'll do, I'll construct a new function. So define z of x to be, I will, in terms of f, I will consider a new function which will vanish at f0 and, at 0 and 1. So what you do from f, you simply subtract a linear polynomial whose values are f0. At 0 it is f0 and 1 it is f1. So what you do is, that is easy to write down. So you simply take something called convex combination. So you take 1 minus x times f0 plus x times f1. You can clearly see that this is again a continuous function, right? Because I have just substituted a linear polynomial from f. And if you substitute x to be 0, so what do you get inside the bracket? You get f0, the second term is 0. So so immediately you can see that z0 is 0 and z of 1 is similarly f1 minus f1. This is also 0. So given epsilon, so Weierstrass theorem you can apply. So let epsilon greater than 0 be given. By the special case, there exists a polynomial q such that mod of zx minus qx is less than epsilon for all x in 0, 1, right? But now you replace g by its definition. You substitute. So g is, remember, f minus some linear polynomial, which is this guy. Let's call this, say, ax. Okay, so this implies fx minus some polynomial ax minus this q is already there. Okay, I can put them together actually, and this is less than epsilon. This is for all x. You are done, right? Because you define p to be all this p. Then you are done. So f minus p is less than epsilon. Okay. So this takes care of the case when f is a continuous function on 0, 1, but it need not vanish on 0 and 1. So now how do I go to a general interval? Maybe I should leave that as an exercise. That is again very simple. So now f from AB to R continuous. Okay. So what you have to do, you have to come up with some function in terms of f, but on 0, 1. You can come up with any continuous function g on 0, 1 in terms of f. You don't have to now have, so I have already reduced the case that f0 is 0 and f1 is 0. That is not required, right? Can you think of some continuous function z? All you have to do is that, you have to find you have to suitably map this interval 0, 1 to AB, because you want to, so if you can, this is a standard thing. So if you can go to AB, because from here you have the function f. So all you need is you need to map 0, 1 to AB, nicely, so that you have a function on 0, 1. That's easy, right? So you simply look at, so how do you do this? So you look at, if you look at t going to, say, 1 minus t times a plus t times b, this maps 0, 1 to AB bijectively, right? And it is continuous. Its inverse is also continuous. Nice. It's something called homeomorphism. Okay, so then you also define so function zt to be f of this guy 1 minus t times a plus t times b. Okay, so apply Weierstrass theorem to z, and then apply Weierstrass theorem to z to get some q. In terms of t, you will get. Then you simply write t in terms of x. You can so x is 1 minus t times a plus t times b. So t you can write in terms of x. So then you get to get some p of x. This I leave it to you for the details, okay? But this can easily be done, like I have done for the previous case. So this takes care of the most general case as well. Great. So this completes the proof of the Weierstrass approximation theorem. I think it's a good time to now stop. As I promised, I will show my face again, right? Once I complete the task. So let me do that. So I have to start the video. Yes. Finally, I should thank you in case you have attended the whole talk, because this is a recorded talk. So I don't know. You may always go forward and skip, and you attend the talk. Yeah. But anyway, thanks a lot for attending the talk. Let me stop share, and let me stop this recording.